Here are the typical growth rates that we encounter when determining the time complexity of algorithms. So as we've seen, we have log n, linear growth, growth of the order n log n, order n squared, exponential growth, and factorial growth. So the basic inequalities involve the powers. So we have 1 is less than or equal to n, which is less than or equal to n squared, and so on, for all the natural numbers. And we also have inequalities for the logarithms. So as we've seen in a previous video, 1 is less than or equal to log n, which is less than or equal to n for all n greater than or equal to 2. So if we combine these inequalities, we get 1 is less than or equal to log n, and that's less than or equal to n, and that's thereby less than or equal to n multiplied by log n, which is less than or equal to n squared, and that's less than or equal to n squared by log n, and so on. And using this inequality, an example is log n is O(n) squared, but log n is also order n. So when determining the time complexity of an algorithm, we typically want a closed upper bound and not overestimate the complexity of the algorithm. Now another example is n is O(n) squared, and n is also O(n). And that's because of the equal sign in the inequality. So we know that n is less than or equal to n for all n. And when we have expressions involving multiple functions, so for example 3 plus 4n plus 7n log n plus n squared log n, well, the order of this function is O(n) squared log n, where we take the fastest growing term. Please subscribe, like, and comment to help me reach more students.